Hope you get to hear me now.
So for a warm-up, the first thing, a function f is given by this function on which of the following intervals is f increasing. So to find out when f is increasing, pause the video and give it a try, and then I'll go over it. So first thing I have to do is find the derivative. For 4x to the fourth, we have 4x cubed. For x squared, we have 2x, and then the negative 2 becomes a 0, so we don't bother writing it. And now we have to find out when the derivative equals 0, because that's what we're going to do to find out when it's positive and negative. Essentially, what we're trying to find out is when is this thing positive, that will tell me when it's increasing. If we cared about where it's decreasing, we would find out when this thing also equals negative. So let's go ahead and factor this. So now it's factored. I was able to pull out a, why did I put a 4? So let me fix that in real time. So that's actually a 2, and that's a 2, and that should be a 1. Okay, I must have been out of my mind when I factored this. Alrighty, so the first thing I noticed that this cannot equal 0. There's no way I can put a number in here that would make this negative, which in turn would cancel out this positive one. The only thing that I could put into the x that would make this negative is an imaginary number or a complex number, and that doesn't really get you a 0 for a real function. So let's focus on the 2x. The 2x equals 0 at x equaling 0. If I was to plug in a negative number in there, this entire thing, this would be negative, and then this would just remain positive. So this entire thing would be negative. If I put a positive number in here, then this would be positive, and this, of course, would be positive, so that would be positive. So on which interval is f increasing? It will be increasing from 0 to infinity, not including 0 or infinity. Alrighty, that would be the answer. C. Let's move on to the next thing. So go ahead and answer this now. An equation of the tangent line of f of the graph y equals x plus cosine of x at point 0, 1. Alrighty, so pause the video, give this a try, and then I'll go over it. So the derivative of this guy right here, of this guy, is 1, because derivative of x is 1. Negative sine of x, because the derivative of cosine is negative sine. Instead of writing y prime, I could have also written down the function of the slope at given x's. How about that one? Given that the derivative equals the slope at any given point, might as well just write down the function of the slope. I digress. So when we plug in 0 in here, we would get 1 minus 0. So the slope for this tangent line would be 0, and the point of this tangent line is 0, 1. It's just the same thing as right there. So pause the video, using this information, see if you can get the tangent line of the graph at that point. There are really two options for you to actually go about this. Given that we have a slope and we have a point, you may want to use a point slope form, given that the point and the slope is given, and that's the only thing in the name. The other option would have been y equals mx plus b, and then you would have had to solve for m and then b, and then you would have had it, but this is easier. So let's plug it in. Alrighty, I'm not going to actually fix my mistake, but I was just about to put 0 because m equaling 0, and I'm not in the best stable point of my life right now, in my mind. I just woke up. So 1 minus 0 does not equal 0. It equals 1. So the slope is 1. I'm so glad you guys are better than I am at everything. Alrighty, so let's go ahead and put the correct number. So that would have been a 1 times, and then x minus 0. So my equation would be y equals x plus 1. I just kind of did that in my head. I don't know why I do that when I'm obviously making mistakes. Just double checking. 1 times x is x, 1 times 0 is 0, so I don't care. Moving the negative 1 to the other side would give me a positive 1. Alrighty, so that would be it. That would be it, so the answer would be B. Let's move on. Alrighty, so we already did a little bit of antiderivatives the other day, but let's look at some like this. Now, this is a very difficult integral to do if you were to just try it out without using the U substitution that I mentioned before. The U substitution being let U equal something where its derivative might be able to cancel out something else. So for instance, letting U equaling 2 cosine of 2x won't really be useful for you, but if you let U equal sine, look at all the good stuff that's going to happen. You let U equal to sine of 2x. You're going to get 2 cosine of 2x dx equaling du. And look what we have here. 2 cosine of 2x. And we have dx. That just worked out perfectly. Here's what I mean by that. So where there used to be a sine, you now put a u. So essentially you're going to have u cubed. And that 2 cosine of 2x combined with the 2x, so we're going to put them right next to each other, now will equal you du. So u cubed du is now what you have to integrate, and that's super easy. So just reiterating, just for those who need it, we had the option of letting u equal cosine of 2x. Or we could have let u equal sine of 2x, or we could have let u equal sine cubed of 2x. Letting u equal to sine cubed of 2x would have not given me a du that would have been useful, where I could have gotten rid of all this. Letting u equal cosine, there's no way you would have ended up getting sine cubed to get rid of the sine cubed. So that du is not useful. But letting u equal sine actually solved a lot of problems. So let's go ahead and finish up. You can't just leave it at this part right here. You have to undo what you did with the U substitution, so plug in your u, and you should end up with, well, when you do the integral, you get 1/4 u to the 4th plus c. But then you plug back in, you would get 1/4 sine of 2x to the 4th power plus c. Alrighty, let's move on to the next thing. So here's another example. So we have 50x to the 4th plus secant squared of 2x to the 5th minus 1. Let's look at that 2x to the 5th minus 1. If I take the derivative of that, I know I'm not going to get exactly what this is, but I'm going to get 10x to the 4th. And that's very similar to this. And if I use this, I can just do some stuff to kind of fix the missing parts that I don't have. So let's go ahead and do that. I mean, clearly the answer is already in front of you. But you're going to let u equal x to the 5th minus 1. Your du, when you take a derivative, will be 10x to the 4th dx. So let's compare with what we have outside here. This is going to obviously look nice because that's just going to be a u. But we have a 50x to the 4th. So out of that 50, let's pull 10 away because we only need 10. And the remaining 5, let's put it somewhere else. So over here, here's part of the 50. Here's the other part of the 50. We only wanted the 10 to make it look like the x to the 4th. And now all of this can equal du. All of this is going to be u. And we're going to be able to do some with the secant squared. Now, we are right here. We have 5. The integral of secant squared of u du. But the secant squared, the integral, is tangent u. So that's one of those identities you have to memorize. And now that we have 5 tangent u plus c, you can plug back in. Our u, it was 2x to the 5th. And now it's going to be 5 tangent of 2x to the 5th minus 1. By the way, it was 2x to the 5th minus 1. I didn't see that minus 1 for a second. Don't forget to see. Don't forget to see. This is not it's not a specific range we were given, so you have to keep it general. All right, let's move on. Alrighty, go ahead and pause the video and try this one. And keep in mind, you want to find out if you were to take the derivative, which derivative would kind of equal, its derivative would equal something else. So keep that in mind when you make the decision. Pause the video. 1 Mississippi, 2 Mississippi, 3 Mississippi. And here we bam! Alrighty. So we let the inside equal all of this stuff because we get our du being 2x dx. We almost have 2x dx here. The only problem is there's a 5 we do not need. So we're going to exile a 5. So we used to have a 10x, we exiled a 5, and now the 2x plus 2x dx looks like this 2x dx, almost identical. So let's do some magic. Boom. Alrighty. So after doing some magic, let's go ahead and figure out what this antiderivative is. So go ahead and pause the video and finish the problem. So let's see what I did. I took the 5, added 1 to it, which makes it a 6, divide by it. And then when it came down to it, I plugged in the u back into the, I plugged in for u. Also, although I have a c right here, I did multiply 5 times c, so it would be probably wrong to write c here as well. So I just changed it to a d. If you don't do that, doesn't really matter. I'm okay with it. Alright, let's do another example for u substitution. We have cosecant of 3x, cotangent of 3x. I'm getting a feeling I'm going to be using the cosecant. And let's try that out. The derivative of cosecant 3x is negative 3 cosecant 3x cotangent of x. I'm going to try to arrange where one of these cosecants right here is pulled out to hang out with this cotangent in order to make this work out. So instead of having a cosecant to the 5th, I'm going to have it to the 4th. So leaving one right here. So now I have cosecant of 3x, cotangent of 3x, but I need that negative 3. So I'm going to fabricate a negative 3. So this negative 3 came out of nowhere. But in order to undo this, or to balance it out, I'm also going to put a negative 1/3 over here. Because the negative 1/3 times the negative 3 would actually cancel out. So the universe is now in balance. So all of this equals du. So I'm going to make that substitution. And I have this to the 4th power, so u to the 4th power. And I have my negative 1/3 that I just came up with. So over here, this will be to the 5th, and then 1/5 of u, plug in for u, and the 1/5 and the negative 1/3 will give you a negative 1/15 plus e. So that's how you did this example right here. So make sure you have this in your notes. Alrighty, so for your notes, go ahead and do these problems. I do want to do 1, maybe 2, just 1. But I'm definitely not going to waste my time on doing a problem like this or this. No, I'm not going to do that either. This one is a simpler version of a u substitution, so I might do this. This is virtually the same thing, except it's a 5, not an 8. And this one has a pi in it, but it's the same thing as that. So I'm going to go ahead and do number 28. So before I do number 28, why don't you try it yourself, see how you get. Pausing in 3, 2, 1. So let's see what I have so far. I made the decision to do the cosine, clearly, because its derivative has a sign in it, and I can end up with a u to the 8th power. So I went ahead and made u equal cosine of pi x, which gave me negative sine of pi x, but times pi. Now the problem is I have almost everything. I have sine of pi x dx. So sine of pi x dx. But I need to take care of that negative pi. So what I will do is I will attach a, let me go ahead and use blue. I will attach a negative pi right here. But I'm going to have to put a negative 1 over pi right there, just to balance it out. So negative 1 over pi, oops, whatever. negative 1 over pi, and then an integral of u to the 8, and then du. Because all of this, if you remember, all of this, the negative pi, the sine of pi x dx, all of this ended up being du. And that cosine of 8 of pi x equals u to the 8, because u equals cosine of pi x. Alrighty, looking good so far. So pause the video and finish this problem, please. Alrighty, should have gotten negative pi of 1/9 u to the 9 and then plus c. I didn't bother putting the plus c inside this parenthesis, multiplying by it, then changing it to a d. Didn't feel like it. So this is good enough. Alrighty, and then plug in. We go back to see what we have. We have a u being cosine pi x, right? Yeah. So let's make that adjustment. Here's some magic. Alrighty, and then wherever you saw a u, go ahead and put your cosine. That is it. See you guys tomorrow. But before I stop the video, let me just zoom back out so you guys can do all of these problems. So do all of these problems, please, so you guys are better prepared for tomorrow.